What's up, everyone? So in this video, I want to talk about what the magnitude of a vector is and how you can calculate it. So remember that a vector is defined by some direction and some kind of magnitude. Direction plus magnitude. And we can often visualize these vectors in a number of ways. So in the previous video, again, that video I dropped from 3 Blue 1 Brown, there are a number of ways to represent vectors, and kind of depending on what you're trying to do with them, you would use a certain representation of it. For us, we're often going to represent them with arrows. So for example, this guy. So this one, it points off into some direction, the top right corner of the screen in this case, and it has some kind of magnitude. The way we refer to the magnitude of an arrow of a vector, one is represented as an arrow, is with its length. So for example, these two vectors, and we're going to pretend that they're parallel. The magnitude of this vector, call this one vector A, and call this one vector B. Magnitude of vector A, written kind of like absolute value of A, is greater than the magnitude of B. Okay, so when we write vectors or draw them out as arrows, the direction that's pointing obviously tells you the direction, and the magnitude of the vector is generally its length. Alrighty? I say generally because we're going to see at the end of this video how kind of quote-unquote length kind of loses its meaning. Alrighty, so let's take this vector A, and I'll just recopy it over here, vector A. And I'm just going to extend it. Maybe it actually goes this way. Whatever. Okay, this is a brand new vector at this point, I guess. So remember that we can always break down a vector into its two components, a horizontal component and a vertical component. If we know that, so let's pretend that vector C has some horizontal component C1, and this is often how you'll see it, and then a vertical component C2. And then if it had a third component, it would just be C3 and so on. Now notice, first off, that these C1, C2, etc., they don't have arrows over the top of their heads, because remember that C1 and C2 are just numbers. They're not vectors themselves, they're just values. Now positive negative tells you if it goes up or down or left, right. But again, there's nothing special here. If you're thinking the length of that arrow is just the hypotenuse of this right triangle, you're absolutely correct. So this would be perpendicular, because we've broken it down to a straight horizontal and vertical component. Then the magnitude of C is simply equal to the square root of C1 squared plus C2 squared. And that's just the Pythagorean theorem right there. And that pretty much is kind of the end of the video if you want to just stop there. But I want to talk about how we can do this with 3 dimensions. Okay? So I'm going to draw a vector in 3 dimensions, or at least I'm going to try my best, and I'll be right back. Alrighty, so here I have a vector 2, 3, 6, and so what I've drawn is I've drawn my my 3 axes. So it might have been a while since you've seen this, but remember that at least the way I've drawn it, the axis that's pointing out at you is the positive x-axis. The axis that points off to the right, that's the positive y-axis, and then the z-axis points straight up. Okay. You might have seen it in different orientations, but there is a certain right way and a certain wrong way to do it. This is but one correct way. Alrighty. But when we say this vector has an x component of 2, a y component of 3, and then a z component of 6, this is what that would look like. So we're going to pretend that our vector is starting at the origin. So how does this work? Well, we'll go out 2 units, so I'll just mark it off 1, 2. So this would be x equals 2. So I'm going to draw it in, I guess, red. Oops, red here. Okay, you're not going to change color? Okay, so we're starting off at the origin. We're going off this way. Okay, now we're going to go 3 units in the y direction. So remember, based on perspective here, 3 units in the y direction is this far. 1, 2, 3. So we're going to go off from here. Oops. Let's do that in red here. 1, 2, 3. So I know you're going to have to kind of bend your brain a little bit, but this is in 3 dimensions. So what I've done is I started off at the origin. I've come out kind of out of the paper 2 units toward you, and then just gone 3 units straight to the right. And now we need to go 6 units vertically, 6 units up. So that would be 1, 2, 3, 4, 5, 6. And that's going to be, again, 6 units straight up from this point right here, which would be drawn like so. 1, 2, 3, 4, 5, 6. Right here. So even though it looks like it's actually at the point y equals 1, z equals 4, it's actually not, because it's, you know, actually coming out of the paper a little bit at you. Okay, and so the actual vector is this one right here. And I'm going to draw the actual vector in blue, I suppose. So the actual vector starts off right here and kind of goes up and out of the paper at you like so. The question is, what is the magnitude of vector A? So again, geometrically or visually, that simply just means its length. And you know, you take a look at this problem, it's a little funky. But what's nice is that because we know we're kind of living in this kind of coordinate system where everything's kind of, we make turns at 90-degree angles, we actually have 2 right triangles, and we can use Pythagorean theorem once again. So check this out. Pretend that you're off standing around in the xy plane. So let's pretend you're over here. And you're just staring at this thing right here. What do you see? Well, the picture that you would see would look like this. And I'm going to draw it. Where should I draw it? I'll draw it down here. So this is person A's perspective. From perspective A, what do you see? Well, you see this vertical big red line with a length of 6 because it comes out of the ground 6 units up. This blue hypotenuse, which you don't know yet. And if we were to kind of see where eventually this triangle would meet the ground and have some kind of mystery length, I'm going to draw it in green here, and I'm going to draw that in green right here. Okay. Again, this is a right triangle because that red side length comes straight out of the ground. Oh, okay. The question is, how could I get that blue side length? Well, I wouldn't know that unless I knew, well, I know this red side is 6, but I still don't know what the green length is. Okay, so how do I get the green length? Well, come back over here and let's pretend that you're now, I don't know, floating, I suppose. You're a person up here and you're floating and you're looking straight down. So you would see, and by the way, this would also be a right triangle. You would see this, and this is person B's perspective now. You would see this. A right triangle with a side length of 2 and 3, leg length, excuse me, and then with some green hypotenuse. This you could find just using the Pythagorean theorem, so let's do that. Let's see, this side length right here will be the square root of, let's see, 2 squared, which is 4, and 3 squared, which is 9. So the square root of 13. That means now we know what this side length is. The square root of 13. And now we can find the magnitude of A, vector A, because we know what its 2 components are. Well, sorry, we know kind of, we know how you could get to A by following this other, using what we already know about the first 2 components. So again, these are our X and Y components, the 2 and the 3. And then now we're implementing our Z component. So the magnitude of A, again, just using Pythagorean theorem here, the magnitude of A is equal to, well, the square root of the square root of 13 squared plus 6 squared. And that actually works out 13 plus 36 to be the square root of 49. If I did this correctly, I believe that's true, which is 7, which is really nice. So let's try to generalize this actually. And by the way, this is not just for vectors specifically. What this is essentially the distance formula applied in 3 dimensions. But it really works out to just this. If some vector A has, again, some components A1, A2, A3, it would come out to this. Well, let's see. How did we get this right here? Well, this actually just comes from the X and Y components squared. And so what this is that this ends up being the square root of a1 squared plus a2 squared. So again, all of that is just this. And in the last part, the z component, or a3 squared. And then if I work this out, if I actually square that, I'll end up with just this. a1 squared plus a2 squared plus a3 squared, which is pretty neat. Now you might be noticing, okay, so when I take a two-dimensional vector, I just square the components, square each of the components, add them up, and then take the square root. When there's three components, I just do the exact same thing with all three components now. Now, a vector can actually, we're kind of going beyond the scope of this course, but technically speaking, a vector could have as many components as you want. Again, the meaning geometrically kind of gets lost because I have no idea what a four-dimensional vector would even look like because I can't see things in 4 dimensions. But if we were to calculate its magnitude for whatever reason that would represent, it would simply be the square root of each of the components squared, and there you have it. Alright, so thanks for watching. Hopefully this visual helped explain why the distance formula in 3D is really what it is, and I'll see you in the next video.